Welcome back to our video module on dynamics. We're currently studying forced harmonic motion, and today I'd like to explore one more facet of this already complex phenomenon. Today I'd like to take a look at one aspect of our particular solution to try to understand damping and forcing frequency. What I've done today is copied and pasted our particular solution in teal below. What a lot of people want to understand is the relationship between the forcing amplitude and the system response. And so what they do is they assign a variable, G, for gain, and that is C1 over here, this coefficient that is an indicator of a particular solution, and they divide it by f over k. We see that in this case, if we do that, that we end up with a term that's 1 over the square root of this sum, b squared over km times alpha squared over k over m plus 1 minus alpha squared over k over m squared. And we can see from looking at this that there's some sort of funky thing going on between B, which is our damping, and alpha, which is our driving frequency. In order to understand it, we'd like to draw a graph. And in that graph, we represent the driving frequency on the horizontal axis, and we represent the gain on the vertical axis. A gain of 1 is the situation in which our forcing frequency is really, really low. It doesn't really matter what the damping is at that point. We're just having a really low damping. We've seen this in action already. When we looked at number 5, we saw a really slow forcing oscillation, and we saw the system respond right along with this force. That looks down here like the gain is about 1. Conversely, when we increased the forcing frequency at number 4, we increased it so much that the mass really didn't have a chance to respond to what we were doing. So we know that at large forcing frequencies, at large alphas, we have a really low gain. We don't see that much happen. And in fact, it looks something like this. From looking at our system responses, take a look at number 7. So with number 7, we have no damping, and we're forcing at resonance. So we know something special happens there, because if you notice, the amplitude gets infinitely big. We see that happening in the equation if we make B, say, 0. That's going to be 0. That takes out all of this, in which case we could adjust the forcing frequency. We have a 0 in the denominator, and the whole thing blows up. And we've looked at this previously. If we're really close to the resonant frequency, in other words, alpha is really close to omega r, omega, the resonant frequency, we see this term is still huge. It may not be infinity, but it's huge. And that happens on the negative side when it's slightly less, and it also happens when it's slightly more. And as we see, we get further and further away from the resonant frequency. This number right here gets farther and farther away from 0. So in purple, we have graphed what happens if B equals 0. Now let's imagine that we're going to have a small b. So this term right here is going to be small, in which case, if our forcing frequency is exactly the same as the resonant frequency, this term's going to go to 0, but it's not going to be a 0 in the denominator because we do have a small number here. But we have a small number in the denominator, so we're going to have a really high gain. So if we have a low damping ratio, our response will look something like this. So B is low, is in our teal. And then finally, let's erase that. And then finally, we can imagine in green that we have a really high damping ratio. So now our damping ratio is going to get really high, which means that even if we're close to the resonant frequency, this term, sure, this one will all go to zero. But if the damping is high, this is going to be the governing term. It's not going to affect our response that much. So that's going to say it'll affect it, but not too much, which means we have something that looks like this. So here we could say we'll say it's a medium size, and our original response right down here, and this one we have B is an overdamped system. So in that situation, we can also imagine that we make B really big. It's not going to matter what happens here. We can drive it resonance or not. If this number is big, it doesn't matter what's going on. So in summary, we've taken a look at a graph that has frequency in the horizontal axis. It has system response in the form of gain in the vertical axis, and we're able to see relationships between our damping ratio and our driving frequency with this graph. Hopefully this gives you a little better feel of how damping and forcing frequencies interact in our forced harmonic oscillations. Thank you, and I look forward to seeing you in our next video module.